Maybe I can. Oh, there it goes. I forgot to hit the record button. Oops. You guys got 15 free minutes of homework stuff. All right, I had a request for section 4. Is everybody good on this question? Can we move on to another one?
Yeah, I think so.
Okay. All right, so 8.4, number 2. Let's look at this one all together. Okay, so we have the integral 0 to the natural log 4 e to the t dt over the square root e to the 2t plus 121. Good. All right, so first things first is that we have not really looked at anything that has these exponential functions in it, but that doesn't mean that we can't do the question. We can still do the question, it's just that we may need to substitute into a different variable to get those e's out of there. So before we do anything, we're going to do a u substitution. Now we have to be careful about what we choose to be the u substitution. If I try to let the u be the entire square root, the derivative of that square root is 2e to the 2t, and that would not cancel out with the e to the t dt that we have up top. So we want to choose our u to be something that when I do take the du, it cancels out that e to the t dt. So I'm going to let u just be e to the t. That way du is e to the t dt. And now my e to the t dt up in the numerator will substitute to be du. So now my integral, the limits have changed. You could find them if you want to. It wouldn't be too bad because that would just be plugging 0 in for this t. E to the 0 is 1. And then plugging natural log of 4 in for the t. E to the natural log of 4 is 4. You don't have to find the limits here if you don't want to. I usually don't, but it's okay. Okay, so now the substitution. E to the t dt, that's going to be the du. In the denominator, I have the square root of e to the 2t. If u is e to the t, then e to the 2t is u squared. Okay, at this point, you have a couple of different options. The first option is that we are in section 4, and in section 4 is where I have those, not where I have, but where the book has those trig substitutions. So you could try to do a trig substitution with this, or hopefully this integral that we have left over here is on that integration table. So let me just find that integration table here. And we're going to hope that one of these things matches. Oh, all right, so I see it down here. It's number 21. The 1 over square root of something squared plus something squared, and we get this hyperbolic sine inverse. It does actually work, so if you type this into the homeworks, it will count it right. But of course, hyperbolic sines and hyperbolic cosines is not something that I would ever expect you guys to ever deal with. So let's do it the other way. So if you see that it's not on the table, or if you don't want to deal with hyperbolic stuff, that's when we're going to do a trig substitution. If I could spell substitution right. Okay. So if you guys haven't got to the videos yet in this section, it's kind of weird stuff. What we're going to be doing is thinking about a right triangle. With this right triangle, the square root that I have in the denominator here, I'm going to think of as part of the Pythagorean theorem. Because I have two things that are added together and squared, the way that you get to the hypotenuse is by adding things together that are squared. So I'm just going to set the hypotenuse of my triangle here to be that square root of u squared plus 121. Then I'm going to have one of the legs has to be u, and then the other leg has to be the square root of 121, which is 11. If I just put my angle somewhere, then what I can do is I can find a substitution that sets the angle equal to the u value. whenever you have the two things added together, your substitution is going to be tangent. So we're going to have u is equal to 11 tangent of theta. Great. I think I have my u and my 11 in the wrong spots. Let me just change those real quick. All right, because tangent is opposite over adjacent. So the opposite u over the adjacent 11, and then we just multiply the 11 to the other side. That looks better. Okay, so now that we've decided that that's the substitution we're going to make, u is equal to 11 tangent theta, we have to find the du, because we're changing variables. Du is going to be the derivative of 11 tangent theta, which is 11 secant squared theta, d theta. Another thing that we would probably need some point is u squared plus 121 all inside of a square root. Not even inside the square root yet. Let's just put it outside the square root and see what we can get. So let's just figure out what u squared plus 121 is. Substituting in u, which is 11 tangent theta, we get 121 tangent squared plus 121. If I substitute out 121, I get tangent squared plus 1. With the Pythagorean theorem, tangent squared plus 1 is the same thing as secant squared. All right, so what we get is that u squared plus 121 is the same thing as 121 secant squared. Okay, now let's do all of those substitutions. So my limits have changed again, because if we're going from u to thetas, you could try to figure out what the thetas are, but it's going to be a little bit difficult. I would just redo the substitution at the end, plugging back in to get the u's. Okay, so I have du up top. Du, we said, was 11 secant squared d theta. That's all going to be divided by that square root of u squared plus 121. So for us, that's going to be the square root of 121 secant squared. Okay, cool. All right, so hopefully some stuff will simplify down. It almost always will with these questions. I have an 11 up top and a square root of 121 in the bottom, which is also 11, so the 11s cancel out. I have a secant squared up top, and then the square root of secant squared in the bottom, but that's just one secant, which cancels out with one of the secants up top, which means the only thing we have left over is just the integral of secant theta d theta. This is not something that you can find by hand. This is still something that we're going to need the table for. So let me pull back up the table. Secant theta is here at number 14. So the integral of secant is natural log of the absolute value of secant plus tangent. So the natural log of the absolute value of secant theta plus tangent theta plus c. We're not going to need the plus c though, because we have limits that we're plugging in. Okay, so we're still not done though. This is the antiderivative, but this is the antiderivative in terms of secant and tangent of theta, and we need it to be in terms of u or in terms of x. What we're going to do is go back up to my equations up here and rewrite them in such a way that I could get u's from tangents and secants. The first equation I'm going to use is this one. I do need tangent. I can easily find tangent by just dividing the u over. So this is going to give me tangent of theta is u divided by 11. This equation at the bottom will let me get secant. If I divide the 121 over, that's going to be equal to secant squared. If I take the square root of that, that's going to give me secant. So whenever you take the square root of a fraction like that, take the square root of the top and the bottom separately. So the square root u squared plus 121 in the numerator, the square root of 121, which is just 11 in the denominator. I know I kind of write that small and out of the way, but I hope that's okay. So let's go back into our thing now. Now, re-substituting everything back out. We still have the natural log. Secant, we just said, was the square root of u squared plus 121 all over 11. And then tangent was u over 11. Now that I'm back in terms of u, now I can go back and look at the limits. So remember, the limits in terms of u was going from 1 to 4. All right, we plug 4 into that, and it comes out to be something awful. 4 squared is 16. 16 plus 121 is 137, I think. So we get the natural log of the square root of 137 over 11 plus 4 over 11. That's going to be minus the natural log of plugging 1 in, which gives us the square root of 122 over 11 plus 1 over 11. I don't think you can do anything to simplify that down. I'm pretty sure that's going to be our final answer there. So that one was gross, but there we go. So let me type it into the homeworks just real quick, just to make sure we did get the right answer here. So natural log of the absolute value of the square root of 137 over 11 plus 4 over 11, that minus the natural log of square root 122 over 11 minus 1 over 11. It says that we're incorrect, but I'm almost certain we're right. I think I'm getting it counted wrong because of the way that my square roots look. I don't know exactly how to fix it. I'm just going to ignore the absolute values because I don't think we need them anymore. Let's write it like this. Still kind of wrong. All right, let me see what the right answer is. Okay. Yeah, so this is the right answer. I'm almost certain I did it right. Let's see if I messed up. Oh, I have a minus sign here. That's why it's counting me wrong. So it's all because of that one pesky minus sign. That should have been a plus here. That was my bad. Square root 122 over 11 plus 1 over 11. The reason those over 11s kind of disappear from the correct answer has to do with the natural log stuff. It just turns out that you don't need them. So if I had just made that a plus sign, it would have counted it right. Okay, so I know this was a really ugly question. I know it took me a while to get through that one. Just to kind of go back and do the highlights of it. First things first, we have e to the t's, and we have to substitute those out into something that we can deal with, right? We can't really deal with e to the t's. We need just regular polynomial stuff. So we do the substitution there. Now we have this u squared plus 121 inside of a square root, which is big red flags for us to do a trig substitution. We set up our trig substitution using a right triangle and substituted it out so that we have an integral of just a trig function. We end up with the integral of secant. The integral of secant is not a nice one, so we had to use the integration table. That's where we got the natural log secant theta plus tangent theta. Our next problem is that the limits that we eventually had were in terms of either u or in terms of x. We could have figured out what the limits were in terms of theta, but they would have been pretty awful looking. So we went back to our trig substitution and figured out how to find secant theta and tangent theta in terms of the u's. Substituted those back in, and then we plugged in our limits from 4 minus plugging in 1. Okay, cool. So I hope you guys are kind of writing this stuff out on your own, like in your own notes, and you made it look super nice and super fancy. It's just very difficult for me to do that using this notebook app thing. If you think it would help, what I could do is I could type it up in Word in like a step-by-step thing and email that out, because this is a long question. Is there any questions about this one, though? Do you guys feel like you got it? Or concerns? It would, yeah, it would have taken the hyperbolic answer instead. So going back to this part here, our x would be u and our a would be 11 in this case. So it's just the hyperbolic sine inverse of it'd be u over 11. So you could do sine hyperbolic inverse u over 11 and then plugged in the 4 and the 1. So hyperbolic of 4/11 minus inverse hyperbolic of 1 over 11. This would also be counted right. Yeah, Lauren, I can do that. I'll try to do it tomorrow and get that emailed out to you guys. Maybe I'll do it tonight if I have some time. No problem. Any other homework questions? Sections 3, 4, or 5. Or we could go back to sections 1 and 2. Don't forget we're having another one of these meetings on Thursday as well at 1 p.m. Any other homework questions?
5 for 7?
Section 5, number 7?
Yes.
Okay. Yeah, okay. So, this one, we have the integral y squared plus 28y plus 196 all over y squared plus 196 all squared. So I know some of you probably haven't gotten quite to section 5 yet, and that's okay. I'll still show you how to do this one. Section 5 is all about partial fractions. I'm sure it's been a long time since most of you had seen partial fractions, and if so, that's okay. Okay, what we need to do for this question is we need to separate this one out into its partial fraction decomposition, because maybe in its partial fraction decomposition, it's something that's actually doable. What we have for this one in the denominator is we have an irreducible factor, a quadratic factor, that y squared plus 196. Because it is squared, it's going to get two separate fractions. We're going to get a fraction that's going to have the y squared plus 196 all squared. We are also going to have a fraction that's just going to be y squared plus 196 to the 1 power. Because these are quadratic and irreducible, the the numerator is going to be a linear factor. So some constant y plus some constant b, and then over here is the same thing, just moving on to the next part of the alphabet, cy plus d. We need to figure out what the a, the b, the c, and the d are to make this work. So that's the partial fraction decomposition side of things. To do that, we're going to multiply both sides by the common denominator. The common denominator is this y squared plus 196 all squared. When we multiply it on the left-hand side, it cancels out and we just get that numerator that comes straight down. When we multiply that on the right-hand side onto this first fraction, it cancels out and we just get the numerator. But on the second fraction, one of the factors cancels. We get the cy plus d, and we have the other y squared plus 196. All right, so that step was just multiplying both sides by that common denominator, y squared plus 196 all squared. We're still trying to figure out the a, the b, the c, and the d that makes this whole thing work. I think the only method here that's going to work is going to be to look at the coefficients of the different power functions. So we need to multiply everything out. So I'm just going to leave the left-hand side alone. We're going to leave this ay plus b alone. We're going to FOIL this out. So cy times y squared is cy cubed. Cy times 196 is 196 cy. D times y squared. And then d times the 196. All right, the reason we multiplied everything out there is that now we have a bunch of different power functions, and we can set the coefficients of those power functions equal to each other. So what I mean by that is that we have some y cubes floating around. On the left-hand side of the equation, I don't have any y cubes. On the right-hand side of the equation, I only have a cy cubed. Those coefficients have to match, so what we get for free is that c has to be 0. All right, then we have y squareds floating around. On the left-hand side, I have a 1y squared. On the right-hand side, I have a dy squared, and that's it. So again, we kind of get that for free. All right, then I have some y terms floating around. On the left-hand side, I have 28. On the right-hand side, I have an ay, and I have 196 cy. So remember, we're only grabbing the coefficients here. Now, I already know what c was equal to. From over here, c was 0. So this whole term is 0, which means that I get 28 is equal to a. Finally, we have constant terms floating around. On the left-hand side, I have 196. On the right-hand side, I have b, and I have 196d. But remember, d we found to be 1. So if I plug that in, I just get 196 here, and when I subtract it over, that says b has to be 0. Okay. So this may be a new technique for you guys. I hope it's not that new, this partial fraction decomposition stuff. If it is, just search online, YouTube or something like that for a quick partial fraction decomposition tutorial thing. But I think in my videos I laid it out as best I could. All right, so the whole point of all of that is now if I go back up to here, I have the a, the b, the c, and the d that's going to make both sides of this equation work. So let's just rewrite what we did have. We used to have y squared plus 28y plus 196 all divided by that y squared plus 1, was it 96? Yep, all squared. dy. But now what we have is two separate integrals. We're going to have the integral of that first fraction. That first fraction was ay plus b over y squared plus 196 all squared, where my a is 28 and my b was 0. So this is just going to be 28y plus 0 over y squared plus 196 all squared dy, plus the integral of the second fraction from the partial fraction decomposition. That one was cy plus d over just a single y squared plus 196, where my c is 0, so I have 0y plus d 1 over y squared plus 196 dy. Okay. So that, again, was taking the first fraction and do a partial fraction decomposition with it, splitting it up into two separate fractions that if we did add them together, would add together to be the one on the left-hand side. Now what we need to do is we need to go back through chapter 8 at all the different techniques we had there to figure out what we can do for these two integrals. This first integral is just going to be a u substitution. If I let u be that y squared plus 196, then du would be 2y dy. And if I divide that 2 over, I get 1/2 du is equal to y dy. So that means that this y dy up here, I can substitute out to be the 1/2 du. All right, so just to write it all out, I still have that 28 floating around, but now the y dy is 1/2 du, and then my denominator is just going to be u squared. All right, looking at this other integral. this other integral is actually going to be something that we can find on that table of integrals. So if I pull up the table again, remember it was this one. It was 1 over something squared plus something squared. So it's going to be this, I zoomed in a little bit. It's going to be this 1 over a tangent inverse x over a. All right, so going back to my question. We have 1 over y squared, so y is the x, and 196 as the a squared. I'm pretty sure that's 14 squared. I actually don't know if that's true. Let me double check. Yep, I have confirmed. 14 squared. So my a is 14. So this we can automatically find the antiderivative for. It's going to be 1 over 14 tangent inverse of y over 14. Okay, we still need to find the antiderivative for this other one over here. So 28 divided by 2 is 14. And then the antiderivative of u to the negative 2 is going to be negative u to the negative 1. But don't forget, we don't really care for u to be in here. We're going to substitute that to be the y squared plus 196. And we can also include this other one, the tangent inverse of y over 14 plus c. Was there limits to this question? I don't even remember. No, there was not. So yeah, I'm pretty sure this is going to be our answer here. The negative 14 over y squared plus 196 plus 1 over 14 tangent inverse of y over 14 plus c. Oh, wrong thing. So let me just type that into the homeworks here to see if we are on the right track. So negative 14 over y squared plus 196 plus 1 over 14 tangent inverse of x over 14 plus c. Oh, crud. Did I type in something wrong somewhere? Oh, I typed in an x instead of a y right there. That's why. There we go. Okay, again, I went through that one kind of quick, so let me kind of scroll back around to it. Was everybody okay with the partial fraction side of things, finding the a, the b, the c, and the d there using that algebra technique? Okay, Ian. Awesome. All right, so then we split it up into the two separate fractions. This first one was just a regular u substitution here. Just be careful with the coefficients that come out of that. The second fraction that we had ended up coming from that table. It was one of those tangent inverse integrals. And then after that, you just add the two different antiderivatives together. So is that one all right? Questions about that one? Everybody feel good? Is there any other homework questions you want to look at? Yeah, we can do one more from this section. I want to backtrack a little bit though. Well, maybe not that one. How about this one? Okay, so this isn't even asking us to do the full integral. It's just asking us to expand out the partial fraction. But maybe we'll do the integral, or at least see if it's possible to do at the end. If it's not possible, I won't worry about it. So here we have z plus 2 over z squared times z minus 1. Is everybody okay with me not writing z's? Because look how awful my z's are. All right, let's try x. X plus 2 over x squared times x minus 1. Okay, so the partial fraction decomposition here, we do not have quadratic factors this time. Even this x here is a linear factor that's squared. So you want to think of this as being x minus 0 squared, and then we have x minus 1. Because we just have linear factors, each one of them is going to get its own fraction, but because this one is squared, it's going to get its own fraction for when it's squared, and it's going to get its own fraction for when it just has the power to the 1. That's the same thing we just did in that last example. We had the quadratic thing squared, so we had a quadratic squared, and then we just had another quadratic. Same thing here. X squared, you're going to have an x squared fraction, and you're going to have an x fraction. We still have that other x minus 1 factor. Because it's linear, it's going to get its own fraction, and then that's it. Okay, each one of these are linear, so instead of a linear top numerator, they're all just going to be constant numerators. The only time you want to put one of those ax plus b's or whatever up top is whenever you have an irreducible quadratic denominator. Something like, the x squared plus 5 or something like that. Okay, cool. Now that we have this, we want to figure out the a, the b, and the c that makes this work. And to do that, we're going to multiply everything by this common denominator, the x squared times x minus 1. When I multiply it on the left-hand side, we just get the x plus 2. Everything cancels out. When I multiply it on the right-hand side, the x squareds cancel, the a comes down, and then the x minus 1. When I multiply it onto this other fraction, the b comes down, one of the x's cancel, and then I still have the x minus 1. When I multiply it onto this last fraction, the x minus 1's cancel, but I still have the c and the x squared. All right, if you want to do the same technique that we did last time, we have to FOIL and distribute all of these parentheses away. So leaving the left-hand side alone, distributing the a into the parentheses, the bx into these parentheses, all right, this time we don't have x cubes, we only have x squareds as our biggest power. So we're going to be looking at all of the coefficients that have x squareds. On the left-hand side of the equation, we don't have any, so just 0x squared for the left. But on the right-hand side of the equation, we have a bx squared and we have a cx squared, so b plus c. Let's look at just x functions. On the left-hand side, I have a 1 coefficient on the x. On the right-hand side, I have an a as a coefficient on the x, and I have a negative b as a coefficient on the x. Finally, we also have constant terms floating around. On the left-hand side, we have a 2 floating around. On the right-hand side, it looks like we just have a negative a. All right, so from all of this, we can solve for the a, the b, and the c. We get the a for free. The a is negative 2. If the a is negative 2, I can plug that into my second equation here. I'm going to have negative 2 minus b. So here, I'll write it out. So 1 equals negative 2 minus b. We add the 2 over. That's going to be 3 is equal to negative b. Or we could just say that b is equal to negative 3. If b is equal to negative 3, then the only way for those two things to add together to be 0 is if your c is positive 3. So here's our a, b, and c. What that allows us to do is we can go back up to our decomposition here and plug back in the a, the b, and the c. So what we get is x plus 2 over x squared times x minus 1 is the same thing as it was a, so negative 2 over x squared, plus b, which was negative 3 over just x, plus c, which is positive 3 over x minus 1. This is the answer for this question, because it was only asking us to do the partial fraction decomposition. But let's just pretend that it was asking us to go a little bit further and find the integral of x plus 2 over x squared times x minus 1 dx. What we would do instead of doing this complicated integral is that we would integrate over negative 2 over x squared dx plus the integral of negative 3 over x dx plus the integral of positive 3 over x minus 1 dx. So you're just integrating over the partial fraction decomposition instead, because those are usually a lot easier to do. And we can do these real quick. So this negative 2 would come out. This is x to the negative 2, which has antiderivative of negative x to the negative 1. So I'm doing this real quick in my head, but you're going to get 2 over x as the antiderivative for this one. On to the next one. That negative 3 we would factor out. And then we have the integral of 1 over x. The integral 1 over x is natural log x. Same thing for this last one. We would pull the positive 3 out, and then we'd have 1 over x minus 1. That would technically be a u substitution, but it would come out to be the natural log of x minus 1 as the antiderivative there. Okay, so this is the antiderivative of this. Or you can think of it is that if you took the derivative of this box on the right, it would come out to be that box on the left after you added all the fractions together. But with z's instead of x's as well, because I can't draw z's. My z's look like 2's. Okay, so that's how you do these partial fraction decomposition questions here for section 5. Now these do get a little bit complicated. Not necessarily the partial fraction decomposition part is complicated, but sometimes the integrals that you are left with can be complicated, and you may need to do some of the other stuff that we did back from sections 1, 2, 3, 4, and that's it, right? Sections 1 through 4. Okay, does that help? Does that make sense here with these partial fraction questions? Any concerns or questions about this stuff? Awesome. Getting pretty late. Any other last homework questions? Okay, cool. Well, let's call it here. We are going to have another one of these Thursday at 1 p.m. I'll also make up that video for that one question that we struggled with a little bit and kind of write it out in like a step-by-step thing, make it a little bit more organized than what I got going on here. There is a Chapter 8 practice test in Moodle. So once you've finished up all the Chapter 8 homework stuff, I would recommend working on that practice test. You might even want to start working on it now, at least the sections that you do know how to do. Next week, Section 7 and Section 8 are relatively small compared to these, which is why I'm having the test in the same week. So just make sure you're ready for that. And if you have the time, work ahead in Chapter 8 and go ahead and start working on the Section 7 and Section 8 stuff that's due next week. I've already made the videos for those videos for Section 7 and 8, as well as the Section 5 stuff. I all did this morning, and it's all up and ready to go. Okay, let's end it there, though. Thanks for coming. For those of you that came, and I will see everybody hopefully Thursday at 1. But as always, you can always email me if you have any questions. Okay, bye. See ya. Have a good night.